Hello, and thank you for joining us for today's webinar, Factory Floor Efficiencies Manufacturing Tools 101. My name is Kim Caloran with Stratasys, and I will be your host for today's event. For those of you who aren't familiar with our company, Stratasys makes additive manufacturing systems that produce prototypes and production parts directly from 3D CAD files. Using our patented FDM technology, we manufacture and sell the Dimension 3D printers and Fortis 3D production systems. We also operate Red Eye On Demand, which is an online rapid prototyping and digital manufacturing service. In today's webinar, you'll learn how to better streamline your production facility using proven technology to produce lightweight, durable, thermoplastic manufacturing tools like jigs and fixtures. Now, without further ado, I would like to welcome our speaker today, Noah Zeringer. He is the Senior Applications Engineer with Stratasys. Noah has been with Stratasys for 5 years and in the industry for over 7 years. He has a bachelor's degree in design and engineering from UW Stout and is certified as a Rapid Technologies and Additive Manufacturing Master by the Society of Manufacturing Engineers. Noah, take it away.
Thank you, Kim. We're going to start out today by talking a little bit about terminology. The industry that we're talking about and the applications we're talking about today are all part of additive manufacturing. And additive manufacturing is a process that is typically used to create a part or a tool by building it up layer by layer or growing the part from the bottom up. There are many technologies that do this. All these technologies are similar in that they're driven directly from CAD data, and they use their patented technologies to produce physical models through an additive process. This industry has been known by a number of different names over the years. Some of those names include rapid prototyping, additive fabrication, and 3D printing. Within additive manufacturing, there are a number of different types of applications. Under the additive manufacturing umbrella, if you will, we've got 4 different application types we've called out. On the left, we have the more traditional, more established applications. These are the ones that are traditionally thought of in the industry, and they're the more product development-oriented applications. The first one is concept modeling. This is basically the initial models or prototypes that are used when product concepts are being discussed. The second one is functional prototyping. Typically, these are parts that are used to test form, fit, and function, and to prove some of the product for performance or manufacturability. The requirements are a little bit more strenuous with this application, but still pretty basic. On the right-hand side, we have the manufacturing applications. This is a large area of growth for the industry, and every day more and more people are adopting manufacturing applications, or what we call direct digital manufacturing, DDM. The first one is manufacturing tools. That will be our focus today. Basically, we're talking about a collection of items used to produce, inspect, or handle manufactured goods. This includes a variety of things such as jigs and fixtures, molds, patterns, gauges, templates, etc. Might be known as rapid tooling or rapid manufacturing. And then the final category is what we call end-use parts. Basically, we're talking about parts or sub-assemblies that are used as a final product. This might also be called rapid manufacturing or DDM, direct digital manufacturing. So let's focus on the manufacturing tools side. Manufacturing tools covers a very broad range of items used for a variety of purposes, but all to make products. It could be anything from patterns or molds to inspection fixtures, but today we're going to focus mainly on different types of jigs and fixtures. Because this is a broad range of tools, we've broken out 3 separate categories. The first one is transportation tools, and what we mean by transportation tools is tools used to move products from one area of a manufacturing environment to another. This could be in the form of part carriers used to move parts from a production area or one assembly line to another, end-of-arm tools used to take parts off of, say, an injection molding machine and put them into another area of production or assembly, or simply tool holders used to carry them throughout the manufacturing environment. The second category of tools are the more traditional jigs and fixtures, and these are used in the assembly or manufacturing areas. These could include a variety of work holders, generic jigs or fixtures, or guides for drilling or trimming. It could also include simpler tools, workbook holders for holding work instructions. Manufacturing line pallets, in addition to transporting parts, can also be used to hold them during assembly. And then custom equipment guards and even 5S tools or organizational tools. The final category we've broken out as inspection tools. These are tools used to hold parts while they're being inspected, such as a CMM fixture, or tools used to check parts, such as check gauges and go-no-go gauges. Under this category, we've also got test fixtures. Oftentimes with new products, there are custom fixtures made to do life cycle testing or different component testing. These three categories are all very broad and contain very different tools, but they're all used to help produce a quality product in a quick, affordable, and repeatable manner. Traditionally, jigs and fixtures are machined or fabricated out of either a wood, metal, or plastic material. Like the items that they're used to produce, these tools often go through a design, documentation, and production process. For an elaborate or intricate tool, there may be a prototyping, evaluation, and design iteration cycle to produce one of these jigs or fixtures. On average, the production of a manufacturing tool may take 1 to 4 weeks. This means the process can be slow and expensive, even if designs are kept simple. The traditional process starts out with the design of a part, oftentimes in a CAD system. That design is then outputted into detailed machine drawings, which need to be sent either to an external vendor or to the machine shop internally. At that point, you wait for a quote on cost and delivery, and there may be some dialogue back and forth between the vendor and the manufacturing engineer in order to either make it easier to manufacture or make it more cost-effective. And once everything is finalized, an order can be placed. Once the order is placed, the parts need to be built or machined. Generally, they'll need to be inspected, oftentimes assembled if it's more than one component. And then those parts will need to be tested. If they meet the demands, they can be put into use. If not, you repeat the design iterations as necessary and start the process over, go through that again. So it can be a little bit of a longer process. Some of the advantages of the traditional process are that it's a proven process and it is the industry standard. The surface finish of these parts is typically very smooth or can be if needed. At high volumes, it's generally easy to justify the cost of these processes. And by high volumes, we mean typically over 100 to 1,000 parts. With all the steps in the process and so many people involved, it's easy to see how it can be a bit of a slow and expensive process. If no changes or corrections are made to the part, 1 to 2 weeks can be a lead time, but it can be as much as 4. And if changes are required, that time can double, as with the costs. There are also some design constraints that are associated with some of the traditional processes. You need to be able to design for manufacturability, or take into account DFM, as it's called. When making one-off items, oftentimes these constraints can be significant because the cost of manufacturing can be significant if you go outside of these rules. So it can sort of limit what you can do with the design. Additive manufacturing offers an alternative method for producing some of these tools. Instead of using the traditional methods, the additive process can be used. First of all, this eliminates many steps in the process. None of the detailed drawings need to be created, but it also removes some of the constraints on how the part can be designed. Because we no longer need to take into account the traditional design for manufacturability rules, designers can now create parts that are truly designed to match the needs of their application rather than to match the needs of the manufacturing technology. So let's go over a little bit of how the additive manufacturing process works. You can see on the bottom, we've compared the traditional process to the additive process. In the design phase, traditionally, a lot of drawings need to be created and work needs to be done up front just to get a quote and get parts made. With the additive process, a lot of that time and effort can be saved, because once you've got your CAD data, you can go directly into production of the part and then take that part out to be used. It's also much easier to go back through the cycle and repeat if you've got a new design iteration. The Stratasys technology is Fused Deposition Modeling. It's an industry-leading technology that's been around for a number of years. One of the real benefits is that Stratasys equipment uses production-grade thermoplastics, so it can withstand some of the demands of the manufacturing environment. This thermoplastic material is extruded and deposited in layers. The benefits of this process are that it's easy and it's relatively quick. The materials, as we just mentioned, can take the abuse that's required in a manufacturing environment, and we can realize some of the efficiencies by eliminating a lot of that external work that needs to be done outside of the part design. On the right-hand side of the screen, you can see some illustrations. The material starts in a canister, which comes in a filament form. It looks kind of like the weed whacker trimming string. That filament is fed up to what we call the head, where it's extruded through a liquefier, melted. You can see in the video here, we're building the part layer by layer. This time-lapse video is showing the plastic material extruded. We're building a wrench here. These layers are all put together and bonded, and when we're done, we've got our final part. Supports can easily be removed, and you can put it directly into use. Next, we're going to cover a few customer stories and talk about how they were able to leverage additive manufacturing to improve the design and throughput of some of their manufacturing tools. The first customer is Digital Mechanics. They created a robot gripper that takes parts from an injection mold, removes them, and places them into the next phase of the assembly process. The original design had hoses that pulled a vacuum through the tool to grip the part and hold it while it transported it. This design was a little bit clunky in that occasionally those hoses would catch and they would be ripped off and they would cause downtime while they had to repair the tool. Digital Mechanics came up with the idea of producing a part that had internal geometry where a vacuum could be pulled so that they wouldn't have to have those hoses catch. The downside was that design would have been expensive to produce using traditional methods. Using additive manufacturing, they could produce that design easily. You can see in the right-hand picture, those arms of the yellow tool there, they contain internal channels where a vacuum can be pulled and there's no hoses that can catch. So using additive manufacturing, they were able to easily produce this design cost-effectively and test it. Based on the production method used, they could produce this part in just a few days. They actually put their prototype part into production to test how it worked. And once they validated the fact that it did work, they were able to actually use additive manufacturing as the final production method for this tool. With FDM technology, support material could easily be removed from those internal channels, and sufficient vacuum could be pulled to make the tool work effectively. The next customer story revolves around the Oreck Manufacturing Corporation. Oreck makes a variety of products. Most of their most famous products are vacuum cleaners. But for each of their products, they have about 50 to 70 assembly and inspection fixtures to help produce it. These assembly features are used throughout their manufacturing environment to help them hold, transport, and assemble parts. And the inspection fixtures are used to help them hold parts while they're inspecting first article parts and doing random inspections throughout the manufacturing process. Because they have Fortis machines in-house, they could produce all of these fixtures in-house without having to produce the same type of documentation, and the tolerances that they can hold, plus or minus 0.005 of an inch, are good enough to meet all the demands for these tools and inspection fixtures. They've been able to realize large cost savings with each product just based on the fixture and tool production alone. It only took a few projects for this machine to actually pay for itself. In the inspection area in particular, they realized that they had a backlog of first article parts coming in that needed to be measured. Now, while those first article parts were waiting to be measured, there were tools waiting in other parts of the country or the world that couldn't be shipped until those first article parts had been verified that they met all their design specifications. So what they were able to do is produce FDM fixtures and FDM parts ahead of time that allowed them to set up a program on their CMM fixture and verify that that program was accurate and worked as they wanted it to, so that when parts came in for inspection, they could simply mount their FDM tool on the CMM, place their parts in it, run the program, and then either verify or provide feedback for that part. So they basically eliminated that backlog, and they're able to greatly reduce the product design cycle even, just based on fixing that one backlog. Here we've got a video of the Oreck manufacturing floor. You can see a variety of different FDM parts in this environment that they're using. The white parts in this picture are polycarbonate parts. They're used to hold components. There's a few stands there you can see. The assembly worker just had a part on an FDM portion. There's an FDM wrench, actually. It's a custom tool used to assemble these parts. So as you can see, there's a wide variety of tools. Based on incorporating the additive manufacturing process into your tool designing toolbox, if you will, you can actually create whole new design practices. Because of the way additive manufacturing works, we can really do a lot of things to improve tool design. Because we don't have to worry about some of those design for manufacturability rules, you can improve the design by consolidating parts together. No longer do you have to make multiple components and assemble them just to do it cost effectively. We can design them all into one, produce them at one time. With the FDM technology, you can create an internal, what we call sparse fill, which is basically a honeycombed internal structure. So you can greatly reduce the weight on a tool, and if that's a tool that an assembly worker is going to be using all day, that can really help to improve the efficiency of the process and make their life easier. You can design for the function of the part more so than the manufacturability of the part. It really gives designers a lot more freedom. It also helps with design iterations. Because it's so easy to produce a part and you can do it in-house if you have a system, a lot more people will take the time to make a design change or a design improvement, I should say, and produce another part. In addition to some of those more intangible benefits, there are also some direct financial benefits that can be gained from this, and time benefits. When you're producing the part in-house and you no longer have some of that upfront documentation to worry about, you can get parts a lot faster. We have one final customer story to share here, and it revolves around BMW. BMW has been using Stratasys equipment for a long time to produce manufacturing tools. Some of their original tools, they found they were limited by these design for manufacturability rules. You can see the picture on the upper right-hand side. It shows a fixture produced by traditional methods. You can see it's kind of square, clunky. It was designed to be produced cheaply, cost-effectively, so it was designed in multiple pieces, and it was made out of metal because that was readily available. By changing to using an additive manufacturing process, they're able to create a design that's much more ergonomically friendly. You can see the picture on the bottom right. It's lighter in weight. They took advantage of that sparse fill we talked about, so it's a lot lighter for the technician to handle. And it helps them do their job more efficiently. In addition to them building a better tool, they were also able to save time and money on this particular project. It's cheaper to produce this fixture in-house than the old one, and they can get it done faster. BMW is a huge proponent of using additive manufacturing to produce manufacturing tools. They currently are producing over 400 fixtures using their Stratasys equipment. As you can see on the right-hand side, they've documented some huge time and cost savings for the production of these fixtures. We've talked a lot about the intangible benefits, or the design for manufacturability benefits that you can be gained using additive manufacturing. But we also don't want to forget about the big values, the direct financial values and the direct reduction in lead time values. You can see from this chart that both Oreck and BMW have had some huge savings in time and cost, in addition to the better design tools that they've been able to produce. To summarize, using additive fabrication or incorporating additive fabrication into your tool production process can really help to streamline the manufacturing of these tools, as well as give you an opportunity to really optimize the design of these tools. We've seen a lot of really neat-looking tools that were designed for additive manufacturing that couldn't be produced any other way, that really help people improve the efficiency of their overall manufacturing or assembly process. In addition to these advantages, it's also really been found to help people reduce the production time and cut some of their tooling costs, which is always important. Some of these tools have been found to help people produce a more consistent quality part by having a better tool, as well as improve the overall cost of production or reduce the cost of production and improve their production cycle times.
Great. Thank you, Noah. That was great information. In just 1 minute, we'll take any questions that you may have, and if you think of a question in the meantime, please be sure to submit it through the Q&A panel. I wanted to let you know that after the event ends today, you can find this recording and then also request a sample part and download some other relevant materials by going to the URL www.stratasys.com/tools. Okay, it looks like we have time for questions now. A couple of questions have come in during the presentation, and there's a question here from Mike, who is asking, some of my fixtures have high tolerance specs. What tolerances can Stratasys machines handle?
Okay, thank you. Mike, that's a good question. The Stratasys technology has a stated tolerance of plus or minus 0.005 of an inch, and oftentimes that tolerance is good enough to meet the demands of some of these tooling applications. However, with that said, we've seen customers who have tolerance specs that are higher than that in some cases. And what they've actually done to overcome that is they've built parts that have a near net shape in those high tolerance requirement areas, and then they've actually machined those areas to meet the tolerance specs of their design. So they've still been able to find enough value in using the additively manufactured parts to do it that way, and they've been creative in finding a way around that tolerance by machining those critical areas.
Great, thank you. Here is another question that came in. This one is from Bonnie. Can I use this technology to make metal forming molds?
Thank you, Bonnie. Yes, actually. We have recently worked with a few partners to develop an application for metal forming tools, specifically revolving around hydroforming and rubber pad press tools. Now, because we are using plastic, there are some maximum pressures associated with these, but we've had a lot of success and there are a number of customers using FDM-built tools for their metal forming processes of hydroforming and rubber pad press forming.
Great. Okay, it looks like we may have time for one more question. Rob asks, our final product is made out of polycarbonate. Do you have that material available, and if so, can we use this technology for end-use production of that part?
Okay, thanks, Rob. We actually do offer polycarbonate as a material, and that can be used for end-use parts as well as manufacturing tools. We have a number of thermoplastic materials, as I mentioned earlier in the presentation. We offer a polycarbonate, as Rob would like to use, an ABS material, a PC-ABS blend. We have some ISO-grade materials in the polycarbonate and ABS material families. And we also have some higher-end engineering materials, Ultem and PPSF, or polyphenol sulfone. So they're a little bit more higher temp and higher strength.
Great. And can those parts be used for end production?
Yeah, I'm sorry. We definitely have customers using all of those materials for end production parts. as well as tooling and prototyping applications. Actually, the Ultim 9085 material is FST rated. That's flame smoke toxicity, so it can be used on commercial aircraft and commercial vehicles in an end-use scenario.
Great, that makes sense. Thank you very much. Thank you for all your questions, and if we didn't get to yours live on the call today, we will be sure to follow up with you via email later. At this point, we'd like to thank each of you for your attention also during the presentation, and now we will close out the call, and I will turn it over to our operator. Thanks.